Chapter 7, Section 3, Inverse Matrix. In this section, you will learn what inverse matrix is, how to compute inverse matrix, how to compute the determinant and what it means. An inverse matrix is a matrix that, when multiplied with the original matrix, results in the identity matrix. In simpler terms, an inverse matrix undoes the transformation that the original matrix represents. For a square matrix A of size n by n, the inverse of A, denoted as A superscript minus 1, usually read as A inverse. This A inverse is a matrix of the same size with matrix A, and this equation holds. Here, I is the identity matrix of size n by n, with 1s on the diagonal and 0s elsewhere. If a matrix A has an inverse, we say that A is invertible or non-singular. If A does not have an inverse, it is called singular or non-invertible. As an example, let's take this matrix A. This matrix A is invertible. Its inverse matrix is this matrix. If we multiply these matrices, we will obtain the identity matrix, regardless of the order in which they are multiplied. How to find this inverse matrix will be discussed later. For a 2 by 2 matrix, we can compute the inverse matrix using the determinant and adjugate of the matrix. As an example, let's compute the inverse matrix of this matrix A. We can compute the inverse matrix of this matrix using this formula. The denominator is determinant of matrix A. We can compute the determinant by this formula. This matrix is called adjugate, which is obtained by swapping the diagonal elements and changing the signs of the off-diagonal elements. Not all matrices are invertible. A matrix must meet specific conditions to have an inverse. The first is being a square matrix. Only square matrices can have an inverse. In other words, for a matrix to have its inverse, it must be a square matrix. The second is the determinant must not be 0. A square matrix A is invertible if and only if its determinant is not 0. If the determinant equals 0, the matrix is singular or non-invertible, meaning it does not have an inverse. Let's compute the inverse of this matrix A. First, calculate the determinant. Second, check the determinant if it is non-zero. Since the determinant equals 5, non-zero, the matrix A is invertible. Third, compute the adjugate by swapping the diagonal elements and changing the sign of the off-diagonal elements. Finally, calculate the inverse. Let's see an example of non-invertible matrix. Consider this matrix B. Let's calculate the determinant. Since the determinant equals 0, matrix B is singular and does not have an inverse. So, why does a matrix have no inverse when its determinant is 0? The inverse matrix serves to reverse the transformation of the original matrix. The absence of an inverse means that the transformation of the original matrix cannot be reversed. A non-reversible transformation is one that causes the original state to become indeterminate due to the transformation. For example, a transformation that projects points from 3-dimensional space onto a 2-dimensional plane loses one coordinate information, leading to problems in reverting to the original state. First, let us consider the matrix A and a vector v1 and v2. In a diagram, V1 and V2 form a square with edges along the x and y axis, having a length of 1 and an area of 1. When the vectors V1 and V2 are transformed using matrix A, V1 becomes AC and V2 becomes BD. And consequently, the previous square has been transformed into a parallelogram. Now, let's write down the information needed to calculate the area of this parallelogram. This information can be obtained from the x-coordinates and y-coordinates of the vectors. Using this information, the perimeter of the parallelogram can be broken down in this way. The same color represents the same shape. The area of these colored shapes can be found with these equations using the coordinate information. Using the coordinate information, the area of the outer rectangle can be calculated in this way. The area of the parallelogram in the middle is obtained by subtracting the sum of the area of the colored shapes from the area of the outer rectangle. Now, let's do the subtraction. We can see that the area of this parallelogram is AD minus BC. This is determinant. Thus, the determinant expresses how much the area of a space changes when transformed by matrix A. If the value of the determinant is greater than 1, the original space is enlarged by this transformation. If the value of the determinant is less than 1 and greater than 0, the original space is reduced. If the value of the determinant is negative, the direction of the space is changed. If the determinant is 0, the matrix transformation causes the loss of some of the information in the original vector space. The transformed space becomes less dimensional than the original space. For example, the three-dimensional space becomes a two-dimensional plane or one-dimensional line. And a two-dimensional plane becomes a one-dimensional line. For instance, if we take the earlier matrix B and transform V1 and V2, the transformed space will become a line. Once the space is transformed into a line, there are infinitely many candidates of the original state of the space in the two-dimensional space. So, if a matrix transforms a space into a line, the original two-dimensional space cannot be restored. The inability to restore a two-dimensional space after transformed by a matrix means that there is no matrix that can reverse the transformation. That is, no inverse matrix exists. In other words, a matrix with a zero determinant loses part of the information of the space after transformation, making it impossible to revert the transformation. That is, an inverse matrix, which represents the undoing of the transformation, does not exist. An inverse matrix is a matrix that, when multiplied with the original matrix, results in an identity matrix. An inverse matrix undoes the transformation that the original matrix represents. If a matrix A has an inverse, we say that A is invertible or non-singular. If A does not have an inverse, it is called singular or non-invertible. For a 2x2 matrix, we can compute the inverse matrix using the determinant and adjugate of the matrix. A matrix with a zero determinant does not have an inverse matrix because it loses part of the information of the space after transformation, making it impossible to revert the transformation. Thank you for watching. Please thumbs up and subscribe to my channel.